Have you ever thought about how a single molecule makes a choice? Well, today we are diving deep into the world of organic chemistry to see just that. We're looking at a family of molecules called halogenoalkanes and the incredibly elegant, high-stakes decision they face during a reaction. It's a story of two completely different destinies.
So, here's what we've got lined up. We'll kick things off with the big mystery. Then, we'll meet our key players, the halogenoalkanes. After that, it's the main event, a showdown between two reaction types, SN1 and SN2. We'll figure out what makes a molecule choose its path, look at some surprising plot twists, and then we'll connect it all back to the real world. Ready? Let's get into it.
You know, every great mystery starts with a puzzle. And in chemistry, that puzzle is often about predicting what's going to happen next. For these molecules, it all comes down to their shape and how that shape can radically change.
So here it is. How is it possible that one reaction can totally flip a molecule's 3D structure, while a different path creates a perfectly scrambled 50-50 mix of its mirror images? It all comes down to the mechanism, the step-by-step dance the atoms perform. And to really get that dance, we have to meet our star performer.
Okay, let's bring out our main characters, the halogenoalkanes. These guys are absolute workhorses in the world of organic synthesis, and their pretty simple structure hides some really complex and fascinating behavior.
So what are they? Well, it's pretty simple, really. You just take a basic hydrocarbon chain, like methane or ethane, and you swap one of its hydrogens for a halogen. That X you see there stands for fluorine, chlorine, bromine, or iodine. This one little change is what sets the entire stage for all the action that follows.
Now, the secret to why these molecules are so reactive is all in that carbon-halogen bond. See, halogens are really electron-hungry, so they pull electron density away from the carbon atom. This leaves that carbon with a slight positive charge, turning it into an irresistible target for things we call nucleophiles, which are just molecules rich with electrons looking for a place to bond. We also sort these halogenoalkanes based on how crowded that target carbon is, primary, secondary, or tertiary. And that crowding, as you're about to see, changes absolutely everything.
All right, our players are on the field, so it's time for the main event. We're talking about the two competing paths a halogenoalkane can take when a nucleophile comes knocking. This, right here, is the heart of our story, the SN1 versus the SN2 mechanism.
First up, we have the SN2 reaction. That 2 means bimolecular, because the most important step, the one that determines the reaction speed, involves two molecules colliding, our halogenoalkane and the nucleophile. It's a swift, totally coordinated move. The nucleophile attacks from the backside at the exact same moment the halogen leaves from the front. One single fluid motion. It's all over in a flash.
And the result of that backside attack is dramatic. The entire 3D arrangement of atoms on the carbon flips. They just snap over to the other side. It's exactly like when a strong gust of wind catches your umbrella and turns it inside out. This total flip is called an inversion of configuration, and it is the unmistakable signature of an SN2 reaction. But the SN1 mechanism, that's more of a two-act play. The 1 stands for unimolecular because the slow, rate-determining step only involves one molecule, the halogenoalkane itself. In Act 1, the halogen just leaves, all by itself. This creates a flat, positively charged middleman called a carbocation. It's only then, in a very fast Act 2, that the nucleophile finally shows up and attacks that carbocation.
And the shape of that carbocation is absolutely key. Because it's flat, think of it like a pancake. The nucleophile can attack from the top or from the bottom with an equal chance. And what does that mean? It means you get a perfect 50-50 mix of both possible mirror image products. We call this a racemic mixture, and because the two mirror images cancel each other's effects on light, the mixture is optically inactive.
So, let's put them head to head. SN2, one quick step, backside attack, a total flip in shape, and it's loved by primary or less crowded molecules. Then you've got SN1, a slower two-step process, that all-important flat carbocation in the middle, a scrambled 50-50 mix of products, and it's the go-to for tertiary, or the most crowded molecules. This chart really lays out the differences perfectly.
Okay, so if a molecule has two different paths it can take, what actually makes it choose one over the other? You might be wondering, is it just random? No way. There are some very powerful chemical reasons behind the choice.
It really boils down to this classic battle, access versus stability. For the SN2 reaction to happen, it's all about having a clear path to the target. A primary halogenoalkane doesn't have a lot of bulky groups getting in the way, what chemists call low steric hindrance. This gives the nucleophile a wide open lane for that backside attack. But for the SN1 reaction, it's all about creating a stable intermediate. A crowded tertiary halogenoalkane is great at this, because all those extra groups help stabilize the carbocation, making it way easier for the halogen to just leave in the first place. So is it easier to attack, or is it easier to form a stable intermediate? That's the choice.
But there is one thing that affects both pathways. No matter which route is taken, that carbon-halogen bond has got to break. And as you can see right here, the weaker that bond is, the faster the whole thing goes. The bond to iodine is the weakest of the bunch, so iodoalkanes react the fastest. The bond to chlorine is the strongest, making those reactions the slowest. Simple as that.
Okay, time for a quick pop quiz to make sure we've got this locked in. We've been talking a lot about nucleophiles. Which of these statements is always true for a nucleophile? Is it A, it attacks a double bond, B, it has a lone pair of electrons, C, it is a single atom, or D, it is negatively charged? Go ahead and think about it for a second.
And the answer is B. If you picked B, you got it. A nucleophile is literally a nucleus lover. It's looking for positive charge, and to form a new bond, it must have a lone pair of electrons to donate. Now, they are often negatively charged, like a hydroxide ion, but they can also be neutral, like an ammonia molecule, as long as they have that available pair of electrons.
All right, like any good story, this one has some plot twists. You know, chemistry isn't always as clean as just picking path A or path B. Sometimes other things can happen, and there are some really interesting exceptions to the rules we've just learned.
For instance, if you change the conditions, sometimes the nucleophile decides to act like a base instead. It'll just rip a hydrogen off a neighboring carbon, causing the molecule to form a double bond. We call that elimination. And get this, if you attach a halogen directly to a stable benzene ring, that bond becomes super strong and basically unreactive to these mechanisms. And for a final twist, some primary molecules, the ones that are supposed to love SN2, can actually go through an SN1 reaction. This happens if the carbocation they form is stabilized by a cool property called resonance, which helps spread that positive charge out. So yeah, chemistry always keeps you on your toes.
So we've walked through the mechanisms, the deciding factors, and even the exceptions, but why does any of this molecular decision-making actually matter? Let's zoom out from the tiny world of the lab bench and look at the big picture.
The short answer is, this is how we build the modern world. Being able to control whether a reaction flips a molecule's shape, scrambles it, or does something else entirely is absolutely fundamental. It's what allows chemists to precisely build the complex molecules we need for life-saving drugs, advanced materials, and basically countless other technologies. This is the essential toolbox for making new things. But this chemistry also has a much darker side. Think about chlorofluorocarbons, or CFCs. Way up in our atmosphere, powerful UV light from the sun has enough energy to snap their super stable carbon-chlorine bonds. This unleashes a chlorine radical, a really reactive atom with an unpaired electron. And this radical acts as a catalyst, setting off a devastating chain reaction that just rips our protective ozone layer to shreds.
And because that chlorine radical gets regenerated at the end of every cycle, it's free to go on and attack another ozone molecule and another and another. Just one of these chlorine radicals can destroy thousands upon thousands of ozone molecules. It is a powerful and honestly a pretty sobering example of how the fate of a single chemical bond can have consequences on a planetary scale.
So we've seen how the structure of a single molecule really does decide its destiny, leading to a perfect flip or a random mix, a new medicine or an environmental crisis. The rules that guide this choice are just so elegant and so powerful. So the next time you see a chemical structure, I hope you look at it and ask yourself, what's its story? What path is it going to choose? Thanks for watching.